Number 2. Reduction of pyridine. Reduction is the addition of hydrogen atoms. A maximum of 1, 2, 3, 4, 5, 6, 6 hydrogen atoms can be added to the molecule of pyridine. 5 of the hydrogen atoms would be added to carbon atom and 1 of the hydrogen atom would be added to the nitrogen atom. 6 hydrogen atoms means 3 molecules of hydrogen can be added to a molecule of pyridine. To commence the reaction, the hydrogen is pressurized through the finely divided nickel catalyst. Nickel has an atomic number of 28. Its electronic configuration from 1s2 to 3px to 3p6 is similar to that of argon. The number of electron and the arrangement of electron in the ensuing orbitals, which are 3d8 and 4s2, are unique and specific to nickel. For a much lucid understanding, we have drawn the orbital picture of the electronic configuration. As we can see that there are 2 half-filled empty orbitals in the 3d8 orbital, and it also has a 4s2 orbital which is fully filled. However, the 4s2 orbital is far from the nickel nucleus, and therefore it is under the least influence of nickel nucleus. That is, the electrons in the 4s2 orbital are free to move. They move freely and they are under the least influence of the nucleus. Therefore, under the conditions of very high temperature and very high pressure, it is obvious that the electrons in the 4s2 orbital are knocked out. In this situation, the nickel would exist in its oxidized state, which is Ni2+. This is an electron deficient state of nickel, and it is this electron deficient nickel that attracts the electrons that are shared in a covalent bond between 2 hydrogen atoms towards it. This attraction of electron pair towards the nickel weakens the sigma covalent bond between the hydrogen atoms. Further weakening is bolstered by the very high temperature and very high pressure that are used in the reaction. The net effect of these two is that ultimately the hydrogen molecule dissociates into hydrogen atoms with 1 electron each. The hydrogen atoms with 1 electron each, they go for a covalent bond formation with the unpaired electron in the empty orbital, resulting in the formation of nickel hydrogen sigma covalent bond. In the next step, the pyridine, which is in its liquid state, is gently passed over the finely divided nickel catalyst. For the reason that nickel exists in its oxidized state, that is, it exists in its electron deficient state, the nickel would attract the pi bond that exists between each of the atoms in pyridine. Further, very high temperature and very high pressure would weaken the pi bond. The net effect of these two is breakage of the pi bond. With the result, each of the atoms of pyridine would get 1 electron each, and it is this 1 electron that is shared with the unpaired electrons in the 3d8 orbital of nickel that result in nitrogen nickel and carbon nickel single sigma covalent bond. Now, a point will come in the reaction process when the temperature would be lowered and when the pressure would be lowered. It is at this point that the nucleus and the electrons would have lesser energy. They would attract each other with lesser intensity. It is at this point that nickel would have very less influence on the electrons of its 3d8 orbital. Considering also the fact that nickel is very far away from the 3d8 orbital. The carbon, which has actually shared its electron with the electrons of the 3d8 orbital of nickel, also feels less attracted towards nickel now. Therefore, the carbon and the nitrogen would take away the pair of electron, resulting in negative charge over each of the atoms of pyridine. The hydrogen nucleus, which is in very close proximity to the pyridine ring, does not lose the opportunity and would leave its pair of electron with the 3d8 orbital of the nickel and attack each of the negatively charged atom in the pyridine ring from below the plane of the molecule, that is from one side, to yield pyridine. Such type of addition from one side of the molecule is referred to as syn addition.